talk about negative dark energy, which is kind of a speculative title to have. And what is holographic dark energy is going to be my first slide. So, dark energy, as you know, it's kind of like an exotic fluid which people introduce in order to explain the late time acceleration of the universe. But what we need is something as simple as a cosmological constant to explain that. But with cosmological constant, we have so many problems associated with it, such as the coincidence problem, fine-tuning problem, etc. And even if you take the concordance lambda CDM model, it also comes with several kinds of tension, such as the Hubble tension, SI tension, and so on. So the question is, can we solve it with the dynamical dark energy? Has always been an option. So holographic dark energy density is a proposal which goes like this, where we have a dark energy density, and this MP square takes care of the units and everything, and L here is the IR cutoff. So this was proposed in a sense where if you want to do a quantum field theory calculation, and a general relativist would not come and argue that you are doing something wrong. So this comes from something called as a CKN bound, popularly known as the Cohen, Kaplan, and Nelson bound. And although the exact origin of holographic dark energy can be a little speculative and we can argue against it, but it kinds of work. So let us see why it works and how it works and what are the perks that we get from it. So we start with the standard Friedman metric, Friedman limit, the Robertson-Walker metric, and obviously we have the Friedman equation. So we are not going to consider any kind of modification to the gravity theory, although we can, in principle, we can translate all of what I'm doing into an FOFR theory. But nevertheless, we plug back this dark energy density to the Friedman equations and try to solve it. So we are not considering any sort of exotic interaction between the energy density that we have, like we are not considering dark matter interacting with the dark energy or any other sort of interactions are being considered. We are kind of using the standard Einstein gravity picture. Then the question is, what is the IR cutoff we are interested in? So there are several IR cutoffs, and the popular one is always the Hubble radius, and you can modify that with the apparent horizon if you are working with a non-flat universe. But then again came the question of causality. There is also options for particle horizon, future event horizon. All these can be a possible cutoff which can be included in the dark energy density definition. But then again, due to the consideration of causality and several other factors, Granda and Oliveros came up with this IR cutoff, which I am going to call as LGO, which has the Hubble parameter and its derivative in the picture. And alpha and beta are taken as constant, but although that can have dependency on the redshift. But that will be a much more general case. And then we define the Granda-Oliveros holographic dark energy, and we substitute back into the Hubble parameter. Then we have a differential equation of this form, which upon solving it, we can solve it analytically, and we can get a definition for the Hubble flow. But the interesting factor is that in principle, at least when you look at this particular expression, equation number 9, you can see that you can almost rewrite this in terms of a WCDM model. But if you were to do that, or in the case that we are going to discuss right now, we see that the dark energy is kind of intertwined with radiation as well as matter. And if you are interested in non-flat universe, you can also have the curvature part also there. But there are special cases. For example, if you take beta to be 2 by 3 times alpha, then interestingly, the matter term decouples from the definition of a dark energy. And if you take beta to be alpha by 2, then the radiation terms decouples, and so on. So what is the value of alpha and beta is obviously the question. And for that, we need to constrain this model using the observational data. That is the typical way how cosmologists work. So for that, we define the dark energy density. For time being, we are not interested in any sort of interaction, although we can do that. But nevertheless, we define the dark energy density by removing whatever matter and radiation components here. We take that out, and what we are left with is the density parameter for the holographic Granda-Oliveros holographic dark energy density. And the equation of state is something that we define like this. But for consistency or for easy communication, we can rewrite, instead of alpha and beta, we can have WZ0 and beta as our free parameters, the additional free parameter. And WZ0 is the present value of the dark energy equation of state, so that we can easily translate what we are getting here to other literatures. Because If you look at the DC result, recently the dark energy equation of state at the present value is slightly greater than that of -1, which is indicating a quintessential behavior. If it is less than -1, it is kind of behaving like a phantom behavior. But interestingly, there are models in which they can be transitioned from quintessence to phantom or phantom to quintessence, called as quinton models. And we'll see what this particular model is telling us. So in order to do that, we take several data sets, obviously. So this is a combination, D4 is a combination of data sets such as the OHT data, which stands for observational Hubble data, the BAO data, the CMB shift parameter, the QSO data. So we are calling it as the D4 data set. And when we do the chi-square analysis, which is chi-square minimization, we have the Hubble parameter, we have the data points, we can fit it and do the chi-square minimization using the standard MCMC tools. And we can see which model is performing better. That is at least a quick check in order to understand whether the model is consistent or not. And we can see that almost all the models are pretty much close, although WGOHD model, which is our model, is slightly favored. And let me tell you why there is two GOHD model here. If you take the present equation of state, present dark energy equation of state to be -1, that is what I am calling as GOHD. And if you put that WZ0 as a free parameter, we are calling it as a WGOHD model. And then we can include the Pantheon data, which is a supernova data, without considering the shoes prior. We can still see that these models are obviously kind of giving similar results. But when we include the Pantheon plus, including the shoes prior, we can see that the model tends to be highly differentiated within the chi-square itself before going to other statistical parameters which can differentiate the model. So we can see that the WGHD model is slightly favored by the Pantheon plus with the shoes prior data. So obviously, the best fit values has to be discussed. So for various combinations of data sets, we can have the matter density, which is consistent with the concordance value 0.3. So I'm writing in terms of 10 to the power -3, that is why it is roughly closer to 300. Then the Hubble parameter, obviously the Hubble tension is not being solved. Whenever I use the shoes prior, I'm getting a higher value of the Hubble parameter. But whenever I'm not using the shoes prior, I'm getting something closer to the TRGB value or the Planck value. But what is very interesting is the value of beta. So the value of beta comes closer to 0.66, which is very close to 2/3. So in the very beginning, I said that when a beta is very close to 2/3 times alpha, we are essentially decoupling matter from the whole picture. And if you take the very first equation and let us say that, okay, radiation is not so dominant in the late phase, we can remove that and we can assume the universe to be flat. This model turns out to be exactly equal to the lambda CDM model. So that is interesting to observe that the value of the beta is very close to 2/3, although it is slightly different. And there is another interesting factor that comes around. This Z dagger is not the transition from the deceleration to acceleration. This is where the dark energy gets from negative value to a positive value. So in order to make that more evident, if the dark energy density is having a transition from negative value to a positive value, which means the equation of state will be having a pole in it, or a singular point will be there. And that comes with extra consequences. So let us see, and another important feature to look here is that whenever the Hubble parameter is slightly higher, that means if we were to claim to have solved the Hubble tension in some way, the redshift transition should be close to 2 or slightly above 2. And I'll tell you why it is. I'm quoting the value 2 of more and over again. So let us see the confidence interval for the free parameters. So we can see that the best fit value for most of the data combination, except for the shoes prior, the beta value close to 2/3 stays within the confidence limit. And the WZ0 value, the present value of dark energy equation of state, comes close to whatever is taken as the standard values in the literature. And we can see that it is mostly lying in the quintessence region, which means the quintessence is preferred. Which also means one can also say that this is supported by the recent DC results, which also prefers a quintessence kind of behavior for the dark energy, although it might have been phantom in the past, but at least in the present, it kind of behaves like quintessence. So this is the confidence contour for these analysis. And I should mention that during this analysis, when we are trying to include the Pantheon data, you have to do an integration in order to fit the model. But when you're doing the integration, it takes up too much time. But then I have to mention that the hypergeometric function, which we discussed in the early morning session, came to the rescue, because that fast snaps the whole process by 10 times faster. So that is one thing that I want to share. So we can have the confidence contour for the other free parameters, and we can also see that the most of the results are slightly inclined towards the Planck values. So we are not essentially solving the Hubble tension, but there is an interesting things that need to be mentioned. But before going to that, let us see other features of the model, which is to validate the model using other statistical parameters like AIC, BIC, and Bayesian inference. And we can see that in most cases, the lambda CDM is taking the golden stand, and there is the other models are not, performing over the lambda CDM model as it was shown in the chi-square analysis, because there is extra parameters coming into the picture. So we need to penalize the model for those extra parameters, and these quantifiers does that. But we can see that whenever you are using the Pantheon Plus data, the WGOHT model is slightly favored, although it is not a strong evidence, but it is something that we cannot rule out. Nevertheless, the interesting facts comes with the dark energy equational state. So this is an analytical expression that you can derive from the previous expression shown, but let us see the graphs. So what we can see is that so anything that goes beyond 0 is kind of like the future, and 0 is the present, and this is the past direction. So we can see that the dark energy equational state kind of starts from 1/3 and then falls to 0 and then falls to -1. So this is kind of like a tracker scalar field. What I mean by that, we know that during this particular redshift, that is of the 1 plus redshift goes over like 1000, that is if you are going into the path, that is radiation domination. So during the radiation domination, the dark energy kind of behaves like radiation itself, because the equational state parameter has a value of 1/3 and then goes to the value close to 0, which means the dark energy is kind of mimicking whatever is inside the bulk. Hence, it kind of captures the true essence of holographic dark energy model. And this is an interesting feature which shows that during somewhere in the past, there has to be a transition from negative to positive dark energy. That is why we have a singular point in the dark energy equational state, because log of 0 is kind of making that singularity there. So does this solve anything? Well, it turns out that there, along with the Hubble tension, which is the popular one, there is some sort of anomaly with the BAO alignment alpha observation. So BAO alignment alpha, so BAO, we are very familiar with the baryon acoustic oscillations. So there are two ways of doing that: observing the alignment alpha forest and also the galaxy clustering. So here I'm using the Pantheon Plus along with the show spray, and we can see that the WCDM and the lambda CDM tends to have some sort of mild tension with the BAO alignment alpha observations. But the GHD model doesn't. So that is an interesting observation. Even if you are not using the shoes prior, that still stands. So one of the interesting features that is been reported recently, including the sign switching lambda CDM model. So we were a transition from negative cosmological constant to a positive cosmological constant happened somewhere between the redshift 2 has been reported widely. And then there are other models where people are considering modified gravity theory like Hordensky gravity and so on. They all show these kinds of features. Although this random holographic dark energy may not be the final answer for everything, although we can still find ways to say that, okay, this construction might be, may not be the most appropriate one. But nevertheless, the fact that it kind of relaxes this tension, or the tension that happens somewhere around the redshift 2 and above, has been addressed recently in several other literature with the common feature that the dark energy being negative. So with that, I conclude this presentation. Thank you.
Hubble tension does not bother you?
In fact, when we try to use the CMP Planck prior for the distance scales, we can in principle solve the Hubble tension. It does use a Hubble parameter of the value of 73, but I'm not reporting that because the present value of dark energy equation of state goes to phantom behavior. So such features are still there. So we can essentially solve Hubble tension using these kinds of models.
Okay. Shaji was our student.
So when I applied for this conference, I was wondering, is there any connection with me to the IMSC? So it turns out that Dr. Shaji,
I taught him.
yes, yes,
He worked with him. They collaborated. He was my first batch of students. Sharif.
he used to tell so many stories about IMSC, and that is one reason for me to apply.
He's a good storyteller too.
Yes, he still is.
Yeah, nice. Nice to see Shajis.